like a nice application. Well, you can put it, but then you still have to do 15 minutes of your own. Oh, come on now, like, what do you want? Huh? Like what I do, proofs, example. It could be like, yeah, like take some application, like I don't know what you're into. Yeah, but it's good to have a focus, like what's your area? Like what do you study? Right, yeah. So take some model from the book or whatever, and just like break it down. Minimizers, Hessian, you know. No, you don't have to make something else. You can read, okay, yeah, you can read from a book. Like you can find some online presentation. You can do that. But then it has to be good. And writing things down. Yeah. Yes, yes, absolutely. Yeah. Yeah. You just take it to someone. But it has to be you. Please don't put like a YouTube clip or somewhere. Yes. That's all learning experience. You just transferring. You have to like, yeah. All the time. I haven't decided. It will probably be two. But we can talk about it. 2 hours is too much, right? Yeah, 2 hours is really the. Yeah, finally. Zoom. People on Zoom, can you see me? Hi, everyone. Yeah, but it's a bit muffled. Daniel, I went to Zoom forum. There is no sound notification. There's some error. I don't know how to fix it. I will have to keep checking. But if you have a mic, please use it, Daniel, because you have good questions. And all of you. Okay. Yeah, we'll continue. Any questions that I need to know? Administrative questions? Oh, can you hear me now? Can you hear me now? No. Okay, good. Do you have a question? Administrative question. So some people asked about the presentation. What should we say? You can take the presentation content from somewhere else, but it has to be presented by you in your own image and likeness and words. Okay. Does it have to be? Yes. We're a fourth-year course. We're adults. Imagine this is like a job interview. Okay. So. Yeah, like in your, what do you think? If you go to a job, you'll be like, does it have to be 50 minutes, boss? Can I just do like a 20-minute thing? And okay, good. All right. No more questions. Good. Yeah, this is terrible. All right, let's go. Well, I mean, all the information is in the syllabus. So Unless you have a question, I don't have much to add. Yes. All right. Let's go. Okay, locally convex. What is that? It shows up in one of the problems. Let's talk about it. All right. A function is locally convex when you can find some radius around that point, so that the function restricted in that neighborhood is convex. So here's a stupid example. We did this a few weeks ago. So it's like, does something like this, it jumps down and it goes up and then down. Can you give me a region of convexity for Z1 and Z2? What do you think? Or should I cut it off? Huh? What? So your background is amazing. Like you have all that. Wow, this is like a word course for you, like a. All right, good. Yeah. This is one, and that's the other one. Okay, so BR1 Z1 and BR2 Z2. All right. Good questions. And we have the following result. You don't have to have convexity everywhere. Pick a point inside and suppose it's stationary and it's locally convex, the function. Then this is a local min, okay? So, going back to the thing we just had, actually the other guys were locally concave. I don't know what the hell we're talking about. This guy is convex. Line is underneath. So yeah, this point Z0 is a local min. Because then it goes down like this. Yeah. All right. Okay, let's prove this result. Locally convex. The translation is you have this Taylor result. So let me explain how you get this. Use mean value theorem. All right. X minus X naught plus your, let me just write it as V because it's boring. Square f of X naught V. And you have that this X guy is in the ball, and that in that ball, this guy is non-negative, okay, by convexity, local convexity, okay? So if you do this, you get this inequality, all right? Like that. All right. So that's one thing. Second thing is, yeah, good. And the second condition just tells us that this guy is 0. Right? This guy is dead. So that's it. Okay. I mean, I know the proof looks very short because all the machinery hides this behind two results. First, the mean value theorem, and that convexity is the same as positive definite Hessian. So there's a lot of results here, right? Okay, good. So again, what we just proved is, like in your quiz question, suppose you have something like this, like it was 2 pi 3 or something. And you computed the Hessian, right? And the Hessian was negative definite, 2 pi 3. And so you got local min. All right. So you basically already used the result without knowing, because we're not very picky. So yeah. Okay. Good. So this was one of the homework questions. Looks painful. Let's do it. I'll do it with you. Can you tell me what's the Jacobian? Like the first entry? What shall I put? Huh? What do you think? Oh, 4x cubed minus 1 times, yeah, and then 2y. You set the 0 to 0, you get y equals 0, and you get x squared minus 1x to 0. So can someone tell me what the solutions are? Yeah, can you tell me what the solutions are? For x? Yeah, I'm asking her. Uh, okay, now let's do the Hessian. Now I feel your pain. What's the, oh, this is going to be terrible. Sorry, what? Well, that was pretty fast. So wait, oh, I see, but wow. So wait, 12x squared, that's one term. And then by product rule, you have the, yes, minus 4, yes, that's smarter. Yes. And second term, yep, this guy, yep. That's not bad. Now let's check for positive definite. So in fact, the eigenvalues will be what? Can someone tell? Oops. Can someone tell me what? Yeah, like suppose you evaluate this at some point x, y. What are the eigenvalues of this matrix? Is that okay? Do you understand? The eigenvalues of a diagonal matrix are the diagonal entries. Okay, good, good. Yeah, I'm just checking, just checking. So this guy is 0, and this guy is what we found. And we ask when are these guys non-negative, right? That's positive definite. And what do we get? X should be what? Huh? X will be what? What? So x squared will be bigger than 1 over 3. And so you get x is bigger than this, or, huh? Yeah, perfect. So you have it over here. No, I'm doing it this way because I don't want to plug in all these points. I'm lazy. All right. So can someone then tell me of all the stationary points, which ones are local min? Huh? Which are the local min? Yeah, so -1, 0. And yeah, the middle guy is, oh, I can even ask you this. Yeah. So what happens at 0, 0? Wait, what? Yeah, it is stationary, I know that. But like, is it max or min? Huh? What? You said neither? No, it's a max. Because what is lambda 1 of 0? It's minus 4. The matrix would be minus 4, 0, 0, 0. So it's negative definite, negative semi-definite. So max. The only place where you have neither, uh, just to be clear, right, is when lambda 1 is this, lambda 2 is this. That's called saddle. And when they're both 0, like, yeah. So when determinant of the, what do I want to say? Yeah, when you get like 0 matrix, so both equaling 0, it's indeterminate. So you have to check by hand. Okay. These are there's only 4 cases. Either it's non-negative, so it's min. It's non-positive, so it's max. Okay, let me write them all. Just you have in one table. Lambda 1, lambda 2. Like that, right? And then maybe plus, minus 0. So if it's plus, what am I doing? What's a good way to do this table? Lambda 1 is plus, and then lambda 2. Huh? Oh, wait, what? I should put the sign on the top. And then lambda 1 is positive, lambda 1 is negative. I'm very you know what, screw this. Maybe the product. How about this? Huh? My table sucks. I'll do this by hand. All right, screw it. Case 1. If some smart person can tell me, I will do it. This is local min. Can you explain it after? Because I'm sorry, I'm confused. And then if you have it like this or the other way, it's called saddle. And then if they're both 0, then it's indeterminate. And you have to check it by hand. All right? Questions? Yeah. All right. That's all you have to do. All right, carrying on. Okay, good. Let's go. Yeah, so the minima are only the ones you told me. This 2, right? And this guy is max. Okay? Yes. Yeah. No, but you can, I'll post this. This is all post. Yes, question. -4.
Yeah, -4.
What? Does it? I hope I didn't. Oh, okay, yeah. Why nobody? What? I wrote 0. Nobody cares. I mean, man, why did you guys tell me? This is all nonsense. I wish somebody told me. So this is a saddle point. Okay. Is that okay? Did you know? You just left me in my misery? Okay. You did? Yeah, you did it. You said it in the beginning. Yes, I didn't. You should like fight back. Fight back. Oh, what are you talking about? Yes, thank you. Yeah. All right, good. So this is a saddle point, and you only have 2 minimum. All right, good. All right, what's the next question? Okay, yeah, so this is a result you'll use many times. If X naught is a local min, then you have this condition, right? Remember? And this is even in the boundary, like we were talking about a few weeks ago. So you can check this anywhere. And if your guy is convex, then you get your global min. All right, so this is the condition that you can get global min. All right, we'll do examples to see how you do this in practice. And you don't have to compute Hessian here, right? There's no Hessian. I don't know if it helps you. I'm just saying there's no Hessian here. Yeah. So, all right. Let's prove this result. As usual, we use mean value theorem, and we use that the Hessian is non-negative over here, right? Is that okay? I still ask you questions. So what can I ask you? But this is non-negative by assumption. And so we're done. Our proofs keep repeating. It's very boring. But okay, yes. So that's why if you just check this guy over all feasible directions. So to be clear, this is feasible direction in case you come back later. Because the examples are more complicated than the proofs, unfortunately. Finding the feasible direction is easy in the proof, but in the examples are a pain, huge pain, as you know. You remember you drew me these pictures and yes. Yeah, like this guy, that would be disgusting. So, do I have the picture? Okay, no. Hopefully you remember this a little bit, yeah? LSC function, it approximates the maximum, yeah? So, we'll return to this. Okay. But then we change the problem a bit, and you'll see why in a second when we go to simplices. But yeah, so I remove this guy, this error. You'll see this next week. Why we do this is called Lagrange multipliers, and this is the Lagrange function we remove. But we'll come back to this. For now, all you have to know is that here's a nice function. Find the minimum. All right, that's the question. Let's find the minimum. Last time we computed the gradient of just the first term, because the second term is just summation of A. So, yeah, so we computed this and it was, we can go review it, but at the end, it was just this guy, all right? Very clean. So if you want me to write it out, this is EX1, EXN, and then you divide by EXI, 1 to N, okay? Okay, that's the gradient. Questions? And yeah, you have to find the stationary points. So, oh, and we also computed the Hessian. Let me write it out in painful detail. So again, you divide by summation of EXI, and you have EX1, EXN, zeros everywhere else, minus summation of EXI squared. And please don't make me write this, but it's terrible. So I always forget this. Z transpose. Right, yes. So it's a generic entries of the form EXI, EXJ, like this. Okay, why is it right like this, please? The IJth entry is just this product. Good. So this was the Hessian, and that was the gradient. All right. What is, yeah, I can ask you this. So, so this is F. F is G minus A dot X. So can someone tell me what is gradient of F? We already got this guy. So just to see if you follow, what should I remove? Yeah, that's it. Okay, good. And what's the Hessian of F? Why just let other people suffer a little bit? Yes, good. All right. Okay, let's play our game. So do I ask the question after? Yeah. So let's do it here. Can someone tell me what's the I'll do it. That's easy. So gradient of F is 0. So then we ask for Z over 1 dot Z to be A. I don't know, maybe you know. Can you give me just, this is a system. Can somebody give me just the first equation? Anybody? First equation? Yeah, what's the first equation? Yeah, like from here, these are vectors. What will be the first equation? When you equate components, what do you get? So Z is EX1, EXN, A is A1, AN. So what's the first equation? Yeah, it's 1 dot Z, dot product. Like this is the summation of EXI. Yeah, good. You know, it's boring for me to just talk myself. So like, I gotta ask you questions. Like, okay, good. All right. So when people ask you find the equations from the first order condition, that's all they mean, and you stop there because there's nothing for you to do. You have to do numerics. Okay, you cannot solve the system using what you know. I mean, if you have Lagrange multipliers, you can do it. We'll talk about this next week. But from here, right, what do? You don't know. But you can just stop here. So these are the equations. Yeah. And we already showed last time that this guy is non-negative using Cauchy-Schwarz, which we proved in 327. Was a nice result. Yes. And it's so we already showed. Yeah, non-negative definite, semi-definite. Yes. All right. Questions? All right. What else? Oh, yeah, this is a nice for your intuition. I don't know how you're gonna use this. So let's review compact sets. A compact set satisfies one of the following. You're gonna see this through the entire term. Um, and if you do any more mathematics, this is like the main object. A compact set, a set is called compact if you give me any sequence. So you give me a sequence xn plus 1, so on, and it converges to some guy x star in the set. Okay? I mean, you take a subsequence, there's a lot of detail there. So I should give you a nice example. Here's a nice example. Take -1 to the n. Does this have a limit? No, right? Okay, can you give me a subsequence that converges? Zoom people, can you give me a subsequence that converges? What about you people? What? Sure. Zoom people? Yes, Daniel, thank you. So even -1, so take n and 2z. Then -1n is 1. So there's your convergence. So, okay, that's the intuition. But the one you mostly will see is closed and bounded. So bounded just means that you can find a big enough ball that contains the entire set. So omega is inside some ball around one of its points. Just take the origin. I don't care. Doesn't matter. Okay. Yeah. And then closed just means that the boundary of omega is in omega. Yeah. Good memories. I can't believe it. Okay, good. Wow, this is like trivial stuff for you. But okay, yes, so this closed and bounded, maybe, yes. Like you've seen this in crazy generality. Yes, that's right, that's right. Yes, yes. All right. Take 0, that's right, yeah. Okay, so I should give you some examples here. Yeah, let's do it here. So let me ask you. So take two examples. How about a 0, 1 open? Is this compact? Why not? Huh? Yeah, it's not closed. So take the sequence 1 minus 1 over n. It goes to 1, but 1 is not in omega. Okay, what's another one? What about the naturals? Like, yeah, natural numbers. Are they compact? So they're closed, and I'll leave that to you because it's very annoying to prove, but not bounded. Right? There is no big enough ball that contains the naturals. The closed is very annoying. Trust me, I remember. Okay, I don't know. If you have something else, we can talk. Yeah. So you can have one or the other. You can have neither, and I'm not going to do it. No. All right, so here's a nice result for your intuition about convex functions. Take a guy to be convex, take your set to be omega, then you have the following called maximum principle. For people who took PDEs, you've seen this. It says that the maximum of the function is attained at the boundary. So let me go back to 1D. Okay. So x squared is convex. Take any interval, like, goes down like this, right? Take an interval, I don't know, -1, 1, and then draw the line. You see that the maximizers are attained at the boundaries, right? Yeah. So f1 is equal to f-1, which bounds f of x for all x in -1, 1, right? And the boundaries here are 1 minus 1. Partial omega is -1, 1. Yeah. So indeed, maximum of x squared in -1, 1 is equal to maximum of x squared in -1, 1, which is just 1 actually. Yeah. Is that okay? Do you understand? Okay, good. Everybody? Yeah. I like simple examples, like that's the simplest thing. And yeah, and the beauty is we're gonna prove this for all dimensions, right? And all kinds of convex functions. Right? I mean, we're not doing minimization. Minimization is tricky. You have to search both inside and outside. Maximization is easy. That's what we're saying here. You don't have to look inside. You can just look at the boundary. So when people ask you maximize, so when they ask you find the maximum of convex in omega, you can ignore interior of omega. Okay? Like in numerical methods, I don't know, whatever you want. So whenever you're searching for the guy, you can just go to the boundary. All right, good. What about for the concave case? What do you think happens? What's the flip side? Huh? The what? What's your, yeah. Yeah, so what would be the opposite? Like, suppose the function is concave. What will be the analogous result? Yeah, so then what shall I, yeah, so sure, but then what will be the result? Suppose G is concave. Yes, thank you. So minimum of omega is equal to the minimum at the boundary. Yeah. Yeah. Good. Yeah, so at the boundary, minimum of omega is equal to minimum. Good, good, good. All right, back to our example. I have some nice MATLAB. So back to this LSC. Again, let me remind you, we studied this because it approximates the maximum function, which shows up recently in neural nets. So I've seen people study it there. The LSC or softmax. All right, so we're going to study this function in the simplex or polytope. So let me write omega. Omega are all x in Rn, so that the xi are less or equal than 1, and they're all 0, 1. Can someone tell me why is this region convex? That'd be too much to ask you. How do you just? I need to know though. How would you check convexity? What should I do? What's the method? How do you start? What's the first step? Take what? Yeah, take x and y and omega, look at x of t, which is 1 minus t. And then what do I have to prove? Yeah, I have to prove this. So I have to check that xt of I is less or equal than 1, right? So let's do that. You open it up. So then why is this less or equal than 1 at the bottom? I know it's easy, I'm just wondering. Yeah, so you have t plus t star, and this is 1. Good. Is that okay? All right, so that's why it's convex. Compact, let me now ask you about closure. Let me ask you, why is this set bounded? Can you give me a bound that contains omega? Can you give me a radius around 0 that will contain this set? Yeah, what? Well, let's give a little bit too. Yes. And what's the reason? So here's why. Take any point in it, x1 squared, xn squared, and actually, how would you check it? It's not easy, right? Like each one is less than, yeah, let me be very brutal. Let me make it square root n. I know, so this would be less than 1 plus 1, which is square root n. Okay? I know it's like containing unit ball, but I have to do it by hand. And whereas here I can just do stupid stuff. Do you understand how to show bounded? Is that okay? Yeah, of course. Please, people, tell me. I don't care. I'm not running for it. Yeah. So how do you show bounded? How do you show bounded? So take any x in omega, which is what? The summation of xi is less than 1, and each of the xi is in 0, 1, right? And you want to show that the Euclidean norm of x is less than some constant r, okay? Right? And then what is this Euclidean norm? Is the one we just talked about, like this. And if you just assume that using this bound that each of them is less than 1, you get 1 squared plus 1 squared, which is square root n, right? Yeah, and then you just let this to be your radius. Okay, so that's how you show boundary. You take a point, you look at the Euclidean norm, and you use properties from your set to build the radius. Yeah, you don't have to get the best radius. You just need a radius to get bounded. All right, questions? Zoom? Questions here? All right, is that okay? Is that okay? Okay, good. All right, so we're in the convex compact. So this function has a maximum, and we need a lot of machinery to find the maximum. So we have to wait 1 week. It turns out that the maximum will just be the standard vectors. So in case you don't remember from other courses, this is this guy. Okay, so at the ith position, you put a 1. Okay, and we'll show next week that f of EI bounds f of x for all x in omega. The proof is long and tedious. So if you find the trick online, let me know, because I searched really hard. But yeah, I wish there was a nice trick. I couldn't find it. I have to use Lagrange. Okay. Questions? Yes. Huh? I said I don't know it next week. Like next week we will prove it. Yeah. Yeah, it's a lot. And I got how I knew it. I started in MATLAB. So I run this on MATLAB. I don't know if you can. Should I take too long? But maybe I zoom in. Oh yeah, zoom in. Zoom in more. Oh, now I'm lost. The hell? Yeah, this is garbage. All right. The red guy is LSC. So summation of log summation of EXI. And this blue plane is the points where summation of XI is 1. And this region over here is where summation of XI is less than 1. Okay, this is omega. Huh? Okay. This is omega. And this is the boundary of omega. And these are the maximum. Okay. And we will prove this next week. So you see that the LSC function has a slope and it hits the maxima at the boundary, like the result tells us. Yeah, that's pretty, eh? In the beginning, I thought the maximum was in the diagonal, but then I ran it on MATLAB and I'm like, no. So, yeah. Yes. Okay, questions? All right. Good. I put the code on your Quarkus. If you want to play with MATLAB, MATLAB is free, I think. Yeah. Yeah. Okay. Yeah, it was free because I remember. I told you guys it's free. Yes. Good. All right. Any comments? No. Yeah, I have to do this next week. I mean, because you haven't. I know you know Lagrange, but I have to review the proof. All right. So again, we're proving the result that maximum of convex is attained at the boundary. Okay. So we'll do this proof, then we'll take a break. Is the proof long? Oh, it's very long. Okay. Have your break. We'll do it after. Zoom people, questions? Yeah, yeah. Yeah. Boundary was okay, right? Yeah. let's all talk about it together. Maybe you guys have a quick way. How would you show it's closed? That's fair for manual. I mean, you can take a sequence and then show that it satisfies the condition, the limit.
Define the
Huh?
define the boundary.
No, closed, I mean, sure, yes, yes. I mean, but that would be overkill. Why not just take the points? Like a sequence. And the sequence would be in 0, 1, because 0, 1 is closed. You take, right? Each 0, 1 for each component. Each of them is closed, but then for the summation, you have less or equal. It was a summation. Yeah. So then the summation will also. I mean, okay, the boundary point will be the plane, like you said. Yeah, so the boundary point will just be the plane. But then how would you prove that is the boundary? Like, isn't that the same as?
I'm not sure. I also want to ask about like the phrase to be the protein. Like,
Okay, wait,
I think that's a different thing.
let's put this one that. Yeah, I will take a sequence. Like that's how we did it in the analysis. Yeah, you take a sequence and we show that the limit point is still satisfying these two conditions. So it's still in 0, 1, and the summation of x star I is less than or equal to 0.
So we have like a subset.
No, just any sequence. Closed means that any convergent sequence converges to a point inside the set. It contains its own limits. So here's the hard part. You can try to prove it.
It's not a number.
Oh, so take because this is a vector, okay?
Okay.
Take xk to some guy x star. Show that first of all x star I is in 0, 1. And show that the summation of x star I is less or equal than 1. That's, yeah.
This is
Yeah. Like this is a vector. And then this is hard. And the way you do it is you add or subtract. And then this guy goes to 0, and this guy is less or equal than 1. It goes to 0. You have to take a limit.
okay.
Yeah.
So
The sequence in K.
so
Oh, yeah, this is a different direction. This is I, and this is K. Oh, right?
okay. So just doing the
In K, between things. Yeah. Yeah, this is also. Okay. If you don't just do it for 1D, just take x, k going to x, and prove that x will be in 0, 1. Put this first. Can you prove this first? 1D. 1D. Can you do this? Well, I'll come back to it. Yes.
not sure about like the
Yeah. First.
things like related to subsequent that part.
Are we able to control temperature?
If you can't do it,
Cold.
No.
how do you change it?
I don't know. Like I think there's thinking,
I'm not like, I have no idea.
thinking you need to
What is where cold? What if we open the door? Is it warm outside?
Yeah.
Yeah. What if it's just, Okay, Max, yeah, go ahead.
About this.
What, did you take 237?
Yes,
Okay, good. You've seen this, right? The closed and bounded. I mean.
yes.
Yeah.
Not the first one.
Yeah, what's the question?
I don't understand it. Like, why? What does it mean? Like, what's the subsequent? Just picking any,
Did I do an example?
yeah, you did,
Yeah.
but why in general?
Oh, I mean, oh, come on, this is like a proof. I mean, it's like, you should take 337 with me. Well, like, I mean, yeah, like,
Okay, so a subsequence is just picking randomly any, like, some arbitrary, like, elements out of it.
yeah, that converge.
So what if it's going in circles?
Yeah, like, or just in -1n, even simpler, like this, jumps around, right?
Yeah,
Oh, yeah,
I'm
yeah.
not sure. What if
Oh,
like
yeah.
somehow
Yes,
it's
yes,
chaotic?
yes. Okay, let me think about this. This is a good question. Take unit circle and take something like EI n pi, right?
Mhm.
Or okay, I don't know. What do you
Okay.
like a rational?
Okay. So you can always just
No,
pick the
wait.
same point? Is that what you mean?
Yes, it will. You will come back. You will come back to. You can pick some guy that will keep hitting. I mean, actually, this is a very difficult question.
Okay, okay.
Um,
Fine, then.
But no, because this is actually a question in real analysis. I remember
Yeah,
it
yeah.
it was a homework question.
I didn't think that.
You take, I think you take like a prime and then times n. Uh, So that you don't, you never like, so I think it was a prime, like a prime number. So that there is no,
Oh, I see, I see.
is it divide by prime or
I
times?
guess it's divided.
Divide by
I don't
prime, right?
know.
Like you never want to,
Yeah, I see what you mean.
yeah, and in this case, we can find a sequence that will do what you said. It will sort of go to some point. You can extract a subsequence. It's not obvious. I mean, I'm not saying it's obvious at all.
What if it's say like the Lorentz system?
Yeah, but I need to see the map. I mean, is it, no, it is true. I mean, as long as you're in a compact set,
Uh-huh.
it's not math. It's not like, it doesn't care how complicated the system is.
That's another question.
Yeah.
Just
Wait, it doesn't have a fixed point, so it does converge. What are you talking about? You have dynamics, right? Oh, you mean like a periodic,
I don't know.
you mean like a horizon attractor?
Yes.
Yeah, the fixed point is the attractor.
Oh.
Yeah.
Why?
Because you have a sequence of,
Why you say converge to the fixed one?
no, it's not one point, it's
Yeah,
the
yeah.
whole set.
Oh, I see what you
Yes.
mean. I see what you mean. Okay.
What's the question?
Like this part.
Uh,
I
well,
don't understand the equality here.
Well,
Like,
you try. What is this less than?
this is, so why don't you just write it like into 1 minus 2?
Yeah, I could, but I'm tired.
Okay,
I could, yeah, but this is less than one.
yes,
This is less than one.
but but this thing. like-
This part is just 1 minus t. I'm just not writing.
Oh, I see. They're all positive.
Yeah.
Okay.
Oh, I see. Yeah. Otherwise, you can't do it.
Yeah.
Did you get it?
Um,
What did you try?
uh,
No, just do one here.
Yeah.
This is obvious or what?
I'm a little confused by the conclusion. So this thing is like a sequence of.
Yeah. Let me write what. So limit of xk going to x means that xk minus x is less than epsilon Okay, bigger than some n epsilon.
Okay.
So then you get to pick your epsilon. So suppose yeah, so you want to put that x is in 0, 1, right?
Yeah.
But then take x to be less or equal than xk plus epsilon. Right, that is. And this guy is less than 1 plus epsilon,
So is this epsilon like?
small number.
Okay, is it like?
No, it's just a number, like 1/1,000. Yeah. And then you have this, and I'll take limits on both sides. We have x, limit in k, 1 plus epsilon, and this is just 1.
Is epsilon just?
Yeah, it goes to 0 because you make it smaller and smaller. So what's a better way to write it? Let me write it this way. Oh yeah, this is analysis. Welcome to and take a sequence epsilon n to be 1/n.
Oh, okay, okay, now I see.
Yeah.
Ah. Huh.
So to take ball analysis.
Yeah.
Take ball, it's pretty cool stuff.
Yeah. I'm not sure.
It's never too late. I mean, are you gonna do grad school or what?
Yeah, most of
Yeah. No, you can take what's your department?
it. Yes.
Yeah, I mean, like us, yes, people do grad school for me.
Yeah.
In physics, but they need it. No, 337.
Oh, 3%.
Like in the summer, I taught 337.
Really? Application in like real business.
I mean, neural nets. I mean,
Neural like
like when you do like the stuff we do now, right?
deep learning.
Yeah, exactly, deep learning.
Ah, okay.
Yes, yes. Okay, I will use the word deep learning. But yeah, I mean, like, yeah, okay, good. Yeah, it's a mess. All right, all right,
Thank you so much.
yeah. All right. Anybody left? All right, some people left. All right, is it cold? I don't know where it comes from. I will ask Diana, our admin. Please make it hot, like really hot. Okay, you guys can make up your mind. Is it hot or cold? Oh, okay, you're one person. I will ask if you can adjust it, and then we will play with it. I will keep going up, down, up, down. Oh, wear a coat. You came in with your shirt. Yeah, wear a coat as well. But I will ask. Okay, I'll ask. Yes. All right. All right, let's go. We will do a survey on the temperature. Like, what's the preferred? All right, we're going to prove that the maximum of omega of f over omega is attained at the boundary. So when you do maximization, you don't have to look far. Just go to the boundary. Omega is compact, so it's closed. Contains its own boundary. So you have the following inequality. Okay, we will prove it both sides. The first one is obvious, just because one is a subset of the other. Okay? And now we want to show that the maximum of omega of f is less or equal than maximum of f in the boundary. So that will give us equal. Yeah? Good. We can ask him later. He probably knows. Take the maximum of f. How do we know the maximum exists? Do you remember from second year calculus? I mean, I will prove it this week, but what's the name of the theorem? You should know really well. But yes, what's the name of the theorem? Huh? Maximum of f exists since omega is compact. Why? Huh? It's called extreme value theorem. Ah. Very good. Do you remember? You didn't do it? Did you do it in 237? No, I'm asking like, okay, but not in 235 either. Let's see. What do they teach you there? Okay, good. That's surprising. Are you sure you didn't learn this? Like that every continuous function is bounded? You did, right? You did?
No.
Thanks. All right. So the picture is here's omega, and we already know it's on the boundary, so, but let me pretend it's not. Let me pretend that it's over here and just take any line going through it. Okay, that's the picture. O is convex, omega is convex. So this is x naught, this is L, and you have points y1, y2. This is any dimension, by the way, because any line in any dimension only hits 2 points. We're in Euclidean space, right? Okay, so only 2 points can be connected by this line. And x naught is in between them, right, from the picture. So you have the following. I'll draw the picture again. X naught is in the middle, y1, y2. So x naught is of the form s y1 plus s star y2. Okay. All right. And good for you. Oh, the proof is long. So we do this. Now we continue. F is convex. So if you evaluate f of x naught on this point, you get this by convexity. Right? Okay, good. And I want to ask you, but what is the guy, what is this less than? Just to see if you follow. Yeah, so it's the maximum, and what was the maximum? No, this was the maximum, right? We said that this is the max. Oh, no, we're not done yet. It's just one step. So this is the maximum. So f of y1 is less than what? Huh? What is f of y1 less or equal than? Yeah, do you understand why? Like this is f of x naught bounds all f of y in omega. What about f of y2? Same thing, right? So what is this equal to, this whole expression? What? Is that okay? You look confused. So go ahead, yeah?
No, I'm good.
Okay, okay. So, but then this is lower bound, this is upper bound. So this is a common trick in analysis. You get that they're all equal. Because, right? Is that okay? And I don't know what to do next. What was the proof? Yeah, this is less than the maximum. So we have what? What are you doing? Oh, I see. Good for you. I don't know. So anyhow, yeah, this is f of x naught, and each one of them is less than the maximum, so maximum at the boundary, omega, plus 1 minus x, maximum at the boundary. So you get maximum at the boundary. So you prove the following: maximum of omega is less or equal than maximum at the boundary, which we proved from before that this is less than maximum of f at omega. I'm just repeating the proof that we just did. Okay. Is it really hot outside? No, I don't know. No, they're cold in here. I have no idea. I don't care. I'll ask them, okay? Are you cold as well from here? I'm sorry. I'll ask them if they can fix that. Yes, they come to your house. They, all right. Okay, good. All right. Let's prove, let's use our machinery to prove the following inequality that we will need next week. It's called Young inequality. The proof is very ugly, but come on. Okay, let's go. So what does it say? It says that A times B is less than this. Do you know Holder inequality, by the way? Yeah, you do. Hopefully you remember it. It's, anyhow. But if you do any more mathematics, you will see this later. So I want to do it here. Okay. The log function is not convex. What am I talking about? It's concave. Who wrote this? Oh, minus log x. Yeah. Okay. I was so confused. So let me prove this. Yeah, minus log of x is convex. Here's why. Take double derivative, and you get minus 1 over x squared, which is 1 over x squared, which is positive. Okay. Good. All right. So you take log of AB. This is very messy. Let me do it with you. So you take log of AB, and you use the product rule for. Let me forget the absolute values because I'm tired. Use the product rule for log, yeah. And then you do the following dirty trick. You get, you do the following. You divide and multiply by P. And then this guy by Q. Okay, and then you use the formula for log with powers. Okay, so you get 1 over P log 1 over A to the P, 1 over Q log to the 1 over B Q. Okay? All right. Now let me ask you. Is it the next? Yeah. So let me ask you. So we know that 1 over P plus 1 over Q is 1. So to make it more familiar, I'll write it as T log of X plus T star. Let me put minuses because that's how it is. Yeah, log 1 over X, log 1 over Y. Since it's convex, what is this? Bigger than by convexity. just this stuff over there. Yeah, so log t over x plus log t star over y. Is that okay? Good. So if you do it for our case, for x equal to AP and y equal to BQ and t equal to 1 over P and t star equal to 1 over Q, you get this beautiful inequality. And then you're almost done. Then what do you have? You have minus log of AB is bigger than minus log of AP over P and BQ over Q. And you move the minuses, yeah? And you get this guy. Yeah. Good. This is called Young's inequality. And you will see it many times in the form of Holder. I'll write it quickly, just at least you see it once in your life. So here's the generalization of that people care about in applications. Take f and g to be integrable functions. And then you have the following. F integrated g is less or equal than the integral of f to the p, 1 over p, times integral of g, q to the 1 over q, and 1p plus 1q is 1. Okay, this is called Holder inequality. Yeah. If you take any, I don't know, where will you see this? I mean, PDEs for sure. Physics, any physics people, you will soon see this. All right. Oh, of course, probability. What am I talking about? I use this all the time. Yeah. Statistics. All right. Like instead of integrals, it could be expectations. I don't know. Are there any statistics people in the room? Oh, you? Yeah, expected value, remember? Yes. No? No. Did you take probability? Here's the one. EXY is less than the pth moment of X times the qth moment of Y. Oh, you know this? What? Oh, I mean, you know expected value though, right? Yeah, I know. I'm advertising. I'm selling inequalities. All right. Okay, good. All right. Let's do a more concrete. Oh, yes. So finally, we're moving past second year courses, and we're starting to do optimization with constraints. Okay. So slowly now we're going to new material. So far, what you've seen is mostly second year. And yeah. All right. So again, we have a C1 function and we have a convex compact domain, blah, blah, blah. This is called the box constraint. Okay. All right. Imagine you have some materials and you can only get these amounts of them, silicon, this, plastic, whatever. And you have a function and you want to minimize over it. This is called a hyperrectangle. I also have seen this in your homework. It's called polytope. Okay, one of the homework questions. Just to give you some practice. Yeah, so just to see if you understand. when is the X star, like a local min, when is it on the boundary? So this is the set. Can someone tell me what's X star satisfying so that it's in the boundary of omega? What should I write? This is if and only if what? If and only what? So can you tell me in detail? What should I write? For at least one, that's what I want to hear. So it doesn't have to be uh, for all of them. It just can be one, and you hit the boundary, right? So the picture, just think of rectangles, right? This guy here is like, what is it? X1, right? This guy is like 1y. And it could be over here, X star, right? And it just has the first component to be 1, right? Is that okay? Okay, good. Because it will get abstract. I just want you to have simple pictures in your head. All right, good. That's good. That's all. So going back to this rectangle, can someone tell me what are the feasible directions? So you have to remember what feasible means. And so suppose X star is over here. Can someone tell me which vectors are the feasible ones? What do you think? Yeah, so you draw a ball like this, and all these guys are feasible. What about over here? Same thing, right? Yeah, so all this, you just draw a ball, center at it, and you can move in all these directions. Is that okay? That's all. So these are the feasible directions, and I will do them with symbols because this is not a proof. So let's work through them. Questions, Zoom people? Right. Yeah, so local min. Suppose that at least one of the xi's is equal to ai, and we want to find the feasible directions. So these feasible directions, let me draw the picture, is suppose this is ai, and this x star is over here, and the feasible direction is any vector that moves like this, okay? So that it's not allowed to be past bi, okay? So it moves up like that, good. In other words, the feasible direction needs to be in this range. All right. Okay. Now let's check the yeah. So the feasible directions are all the vectors that look like standard vectors. EI. So let me write this. This is 0, blah blah blah, 0, VI, 0, blah blah blah. Okay. So when they ask you for feasible direction, that's the one. And to have first order condition, you need the this guy to be non-negative. All right. So let me ask you now to see if you understand. What's the implication for this point for the gradient? Can someone tell me what will be the sign of the gradient of this partial derivative? Zoom people, is it positive or negative? Huh? Yeah, it's positive because VI is positive. So for the product to be positive, you need both of them to be positive. Yeah. All right, good. So yeah, you need the partial derivative to be positive. All right. Now suppose that you are at the upper bound. So X star is up here where BI is equal to XI. Okay, so this is the rectangle, and the X star is at the upper guy. Okay. Now, like you mentioned a few minutes ago, the only allowed direction is down. Okay. So the VI will be a negative number because it has to go down, right? So again, I want you to work this out. So we have VI plus XI star, which is equal to VI plus BI. This guy needs to be less than BI, so it forces VI to be negative. Is that okay? Do you understand? If you don't, I can go in more detail. You have to tell me. I'm not sure if it's. Is that okay? Do you understand? Yes. Yeah. Okay. Thank you. Somebody has to tell me what to do. All right. Again, what does feasible mean? Let's remind ourselves. Feasible. It means that feasible V in Rn. If and only if V plus the minimizer is still in omega. That is the condition. Yes? Right? So that's the condition. And then, yeah, that's the condition. And we know that Xi star is Bi. So we require Vi plus X star I, come on, X star I to be in AI Bi, right? That was the box constraint for the ith component. Okay? But then you know what Xi is. So you write this as Vi plus Bi, subtracted from the interval, and you're left with Vi has to satisfy AI minus Bi, comma 0. Okay? Is that okay? I don't think it's hard. It's just a little bit of algebra. But yeah, you will have homeworks on this, so you'll get a lot of practice and we can talk about this. Oh, yeah. So why is it, I mean, yeah. So what would be the sign of the gradient of this partial and why? And why is that? Okay, yes, all right, great. It's easy, right? Bird course. Good. So yeah, the hard part is the boundary, and yes. And what about, there's one more case left. What if you're inside? What should the gradient satisfy? Yeah, that's all. Okay, so if you're at the boundary, unfortunately, you have to check feasible directions and make sure that it increases. That means your guy increases. And internally, you have a nice bump, but you know, I don't know if you can visualize this, but imagine imagine like a parabola. I should like do MATLAB, but this is terrible. So it goes like this. Okay, goes like this. I should make it with colors. So internally, you can put a tangent line, but at the boundary, you can only put different color. Like this, and like this, and like this, and like this, and like this. This means nabla of f dot v is non-negative. This means gradient is 0. Yeah? Okay, perfect. Good. Gradient is 0. Yes, thank you. Daniel, please get a mic. I want to hear your voice. It would be nice if you can, if you want. No pressure. Oh yeah, if it's furthermore convex, then what? Yeah, so this guy is less than like this by convexity, and this is by first order. So you just have this. So yes, f of x star is local min. If and only if f is convex. So because people might get confused, right? If you're local min, you satisfy these conditions, but if you are convex, it goes the other way as well. So if you're not convex, it could be that these are satisfied, but it's not a local min. And it was one of your homework questions. I think. I'll try to, okay, we'll see. Or, anyways. Questions? Oh, it was in the quiz. Yeah, it could be 0. Anyways. Yeah, so I put the result in a theorem that we just proved. So if you're at the boundary, then if you're a local min, then you need to satisfy these two inequalities, depending on which boundary you are. But if you're inside, you'll just be 0. Okay? And if you're convex, replace all the then by if and only if. Okay, wherever you see then, put if and only if. Okay. So what does that mean for you? It means that if you want to find the local min, find the places where this and this is true, and that will give you the local mins. And it will give you the candidates, but then you have to check that these are indeed local mins. And usually that means using the Hessian, like in your quiz, right? Like in the quiz, you got 3 points, 2 pi over 3, 4 pi over 3, and pi. They were all stationary, so everything is satisfied. But when you computed the Hessian, you got negative positive eigenvalue for pi, so it was a saddle point. So it's neither local min or max, right? Yeah. Okay, good. So I typed the solutions. You can read them. All right. Yes. Why are we not what?
Check the one. AI. Why are you not checking other?
Well, because I need, again, well, remember, I just need to find a candidate. I don't care how you find it. Usually that's the easiest one. You should think about this as, here's a nice machinery to find the candidates, but then you have to verify that they are local mins. But if, do you know what I'm saying? This is only like a guess tool. It's not, of course, but then if you know you're furthermore convex, then you have to check that this is true for all directions, not just the one like this. It's just this one makes my life easier for finding X star candidates. Right? Do you understand? Well, we'll do an example. Let's see. I mean, so again, just to remind you, this only gives candidates. They're not necessarily the men. Okay? Like in quiz 2. So like in quiz 2, x, y equal to pi, was a saddle point. Right? Yeah, okay, good. So these are only candidates. In the quiz, you found the candidates where the Hessian, the gradient is 0, but then you have to use the Hessian to verify. Okay, good. So let's do this quadratic form that you might see. I mean, you can see it anywhere if you do any data analysis. Take the matrix to be symmetric, positive eigenvalues. So it's invertible because it has positive determinant. And take your omega to be this box cube, just a hypercube. Okay. And I even have a more concrete example. So this 2 by 2 matrix, and this is B. What are its eigenvalues, by the way? Anybody? What are the eigenvalues of this matrix? Lambda 1 is what? Yeah, somebody has to answer. Like Zoom people, anybody. I have to know that you know this. What are the eigenvalues of this matrix? Yeah, I'm sorry. If like somebody has, yeah. What are the eigenvalues? Why? Yeah. So if you compute the characteristic polynomial, 1 minus lambda, 3 minus lambda 2, you get 1 minus lambda, 3 minus lambda, which is 0 only at 1, 3. Good. All right. And that's a general fact. If your matrix is hypertriangular, yeah, good. All right. The gradient. We found this last time, but here's another proof because it was very messy. I didn't like it. So I'm gonna do it using the limit definition. All right. So remember, right? We had this result that the directional derivative, so f of x plus h of v minus f of x divided by h is equal to the gradient at x dotted with v. Remember? Okay, good. So if you can avoid partials, please do, because this is way cleaner. And you should use this, it's very nice. So f of x plus hv is this guy, all right? Linear algebra, just bring in the matrix, right? Open it up. So you have by linearity, okay? All right. And do I say, yeah, so let me do it here. So now what you're left with is limit as h goes to 0 of h v transpose ax, h x transpose a v. So let me ask you if you understand this. What do you think this limit equals to? Who survives, who dies? Huh? What? What is it? You guys are scaring me. Yes. Yeah, like the last guy dies out, right? Yeah, the last guy dies out because once they cancel out, you're still left with an H. So it goes to 0. Yeah. I don't know if you're tired or you don't. Like, I'm not sure. Okay. All right, good. So this is what you're left with. Yeah. Which I typed. So, so you get this dot product over here. I should do the middle step. Okay, let me do the middle step. So you have this, and then you can write it as follows. So so you have, what do I want? So this guy is V transpose A plus A transpose X. All right. So this guy is okay. But then you write the other guy as V transpose A X transpose. Is that okay? Something like that. Yeah, okay, anyway. So you do this and, all right, questions? So this is nice because on one hand, you know the directional derivative is V dotted with the gradient of F. So you have these two are equal for every V and you just read off the gradient. Okay, I didn't take a single partial derivative, which got very messy last time. Okay, good. No partials, which get very ugly very quickly. So if you're going to avoid partials, please do use this way. All right. So that means gradient of the function plus the shift, we just add plus B. All right. And in our example, our matrix is symmetric. So you get 2 times, it cancels out with a half. So, okay. This is the gradient of this quadratic form. Is that okay? I'm just plugging in the numbers. Okay, yeah, let me, you look confused. So A is symmetric. So A is equal to A transpose. So you get a half, 2 times AX plus B. So this is AX plus B, right? What? I see wide eye. Is that okay? So what? Yes. Oh, it's not symmetric. Yes. Ah. Okay. I'm sorry. I don't know why I put this to the, you're right. Make it symmetric. Thank you. Yes. Because I don't want to spend hours and hours doing this. Thank you. I will mess up so many. I didn't catch it. Let me see. Can I avoid this? I think. That's painful. I don't think I can avoid it. That's death. Thank you. All right. Let me think. Okay, I know how to fix it. Yeah, okay, so I will have to use the actual thing. So it will be, so this will not be the gradient. It will be a half of 2, 2, 2, 6, and 1, 1. So you can put in the half, so it's 1, 1, 1, 3, plus 1, 1. Is that okay? Yeah? How do I miss this? All right. Yeah, thank you. Yes, exactly. All right. I will retype the entire example, but let's see what we can do. The theory. I want you to see the theory. So what is omega? Omega is the hypercube. So let's stay in in 2D, 0, 1 squared. And suppose that one of the components is 0 for the minimizer. Can someone tell me what are the feasible directions? Huh? You said it before. So what is it? What are the feasible directions? Yes, thank you. Like this. Now let's do it mathematically. So for what we just did before, at the lower bounds, we just ask for the gradient to be non-negative, right? That was our result. Yes. So this is AI. Going back to our result. And painful, so painful. So if A is symmetric, you ask for the ith component to be non-negative. Okay, that's in the symmetric case. And in the non-symmetric case, it will be a half A plus A transpose plus B I to be non-negative, and then X star. Okay, let me put this bigger. A transpose X star plus B I non-negative. All right, that's what you need to satisfy at the lower end. So what was my, yeah, so let me scratch this. I will retype it. So it was 1, was it? 113. All right. So I'll do this all by hand. The hell? All right. All right. Again, we ask for this, and I just showed you that the gradient of G is 1113x plus 1, 1. All right. And now suppose that you have x1, x2. Suppose x1 is 0. Okay, so you're at the lower bound of your cube. Okay. Yeah. So what was our constraint? Our constraint was that the partial G, partial x1 needs to be non-negative. Okay. Let me write this in more clear terms. in terms of partials. So you have to multiply it out. You get x1 plus x2, x1 plus 3x2, and 1, 1. The first component is the first derivative. The second component is the second derivative. Yes? So can someone please tell me if you have partial 1 to be non-negative, what are we saying? Which of them should be non-negative? Huh? Yeah, so you have x1 plus x2 is non-negative. x1 was 0. So you're asking for x2 to be bigger than -1, which is always true. Okay? All right, good. Yeah, I will retype this and upload it. So, right. Now, if x2 is negative, you're asking for, where is it? Yeah, so if xi is 1, from our result that you should read, the block theorem, we ask for partial g partial xi to be negative. Okay, so I'm going to continue this next time. It gives you that A transpose plus BI needs to be non-negative. And yeah, anyways, I'll continue next time. I'll redo this from the start. Thank you.